Welcome back to Math 451, which is our numerical methods class. And we're going to continue looking at the numerical differentiation. The last time we looked at a one-sided derivative and we came up with a computational formula that looked just like the definition of a derivative without the limit. With that, by carefully looking at the Taylor expansion, we were able to identify the error associated with that approximation. The error was linearly related to the h term plus other terms that would disappear more quickly. Now we're going to look at two new methods. One is called the central difference method, and we're also looking at something called the Richardson's method. So let's take a peek at this. Now we're back to our Taylor series again, wanting to see if we can get even more out of it than we did last time. Why couldn't I take a look at f of x minus h? That would be just as good of a secant approximation as the more classic definition. There's really no difference. At least there's no difference in accuracy. So I could write that down. I could also write down this definition of a derivative involving x and x minus h just as easily. This error here is going to still be a order of h error. It will have the same accuracy as the original error that we had in the first approximation. So let's go ahead and write this down as two different equations. So here I've got my original f of x plus h equals f of x plus all of these other terms. I'm listing a lot more of them out now just to make this really clear. And I'm going to write down a second equation, equation 2, that deals with f of x minus h rather than f of x plus h. The only thing that will occur that's different is you'll end up with a minus h in these polynomial terms instead of a plus h. Now, looking at it more closely, if you have odd powers like minus h or minus h cubed or minus h to the fifth, that turns into still a minus h to whatever power you have. But if you have even terms here, where it's like a squared or to the fourth or to the sixth, then the negative sign is going to disappear. So we could write that down and we would end up getting the same kind of form, except we would have alternating series of a minus f prime h plus 1/2 f double prime h squared minus 1 over 3 factorial f triple prime times h cubed, and the signs go plus minus off to infinity. Now we can do something kind of interesting with that. If we take the second form of the equation and subtract it from the first equation, we'll end up getting f of x plus h minus f of x minus h. And as you combine them together, every even term is going to cancel out because they're the same term between equation 1 and equation 2. So now I can just eliminate that. The odd terms added. Notice there's a 2 that appeared in each of these odd terms. Well, how did that happen? That happened because on the odd values, they were of opposite sign. So I have an f prime of x times h minus a minus f prime of x times h. That's the same as f prime of x h plus f prime of x h. And so you get two of them. And so you can write this all down as the f of x plus h minus f of x minus h over 2h on the left. And I am now able to do the same thing I did with my one-sided differentiation formula, and that is to try to isolate f prime. So I've already now got f prime sitting by itself. I've got it set equal to a different computational formula than I had before, with a polynomial whose smallest power of h is h squared. So if we just rewrite that again, here's our f prime of x equals the computational formula, and I subtract all the other junk to the other side, it becomes an error term whose leading polynomial term is second order. Now, if you take a small value of h and you square it, you get a really small value. And so this, what is now called the central difference method, is going to converge at an O of h squared rate rather than O of h. That's going to do way better than the more traditional derivative. And so our error term is order of h squared. This is the actual formulation of that error. Only the leading term matters because the rest of it goes away so fast. And let's try the central difference method using the function x squared. Well, let's just go ahead and expand this out. We can do that. It's easy to take squares. So if I do expand it out, I get this quadratic polynomial, and I get one very similar to it, except I have a minus 2xh comparing it to a plus 2xh. So if I make the subtraction, the x squared disappears and the h squared disappears, and the only thing left over will be 2xh minus a minus 2xh. And then, of course, dividing by 2h. So you end up with 4xh divided by 2h. You're going to get some cancellation there, and the result is going to be 2x plus an error of order of h squared. Now, look carefully at what we got. If you had taken a normal derivative of x squared just by applying your first quarter calculus techniques, you would just look at that and say, oh yeah, the derivative is 2x. We just used a numerical method that will have some error into it, and yet we are getting the exact answer. You know, we came out of this thing with an exact result, no error whatsoever. Well, why did that happen? Well, that happens because when you really do have a polynomial of order 2, a O of h squared algorithm will get rid of all the error, not just some of it. It gets rid of the whole thing. But it's not common that you would be differentiating such a simple function. Otherwise, what's the point? Just differentiate the thing and be done with it. We'll be applying this differential method on highly nonlinear functions, and therefore there will be some real error, but it will do a lot better than our one-sided method did. So let's just take a look at a table now. If we could go into Excel or we could go into MATLAB and see how these two competing methods compare. This time we're going to use a different function. We're going to use e to the x because that it will have some error associated with it. And we know that the derivative of e to the x is e to the x. And if we're going to evaluate that derivative at x equals 0, then we know that the derivative will be e to the 0, or 1. So we're expecting the result to be 1 theoretically. Well, even look at this very first term. Our one-sided method gave us about 1.3. Our central difference method gave us 1.04. Clearly, that's a better result. If we continue to cut the h value in half, so now we'll use a quarter, yes, we do improve the one-sided table, but we also improve the central difference method, staying significantly better than the one-sided calculation does. As you start taking differences of values, like we talked about on the first week of class, as those values become closer together in magnitude, then the difference starts causing numerical error to creep in from the right of the word. The central difference method is not only getting us to the answer quicker, but it is getting us there with less numerical round-off error risk. Your homework is going to have you rebuild this table, and you're going to add another column that does even better than this, but we'll see how that works out when we get there. We are going to continue this idea of eliminating the highest order error term in the Taylor expansion. So let's see if we can't continue that trick, and we will. We're going to call the thing Richardson extrapolation. But let's go back to what drove this. It was a Taylor expansion about f of x plus h. And then we said we could do just as well with f of x minus h, and we notice we get alternating plus and minus signs when we complete the Taylor expansion. So here's what the trick is for Richardson's extrapolation. It's going to start with the same idea as we just did, but we're going to name this central difference method psi of h. Psi of h is going to be equal to the true derivative minus some polynomial that's of order 2, and oh, by the way, it's skipping every other term because all the odd terms dropped off. Just for simplicity, we're renaming all of these terms here on the Taylor expansion because it's just going to be less clutter as we approach this Richardson extrapolation. Here's the idea. We are going to use this over again, this psi of h that we just created, and we're going to create a new psi evaluated at h over 2. So we're cutting the h interval in half. Notice that the one thing that is not impacted is the true first derivative. Everything else is, but that isn't. Okay, let's go ahead and keep going. So here's our psi of h. That's the psi of h we're used to. There's defined up on the right-hand corner. It's equal to the first derivative with all of these powered terms. We're going to define psi of h over 2 to be, of course, the exact same function. It's just that h is replaced with h over 2. So now what we want to do is manipulate or take a linear combination of these two equations in such a manner that the h squared term cancels out. If you did the right linear combination, we could eliminate the lowest order term involving h squared. Since I'm going to get a 1/4 factored out in front of that, if I multiplied the whole lower expression by 4, I would be making those two terms identical, and I could subtract the two equations together and eliminate them. And that's going to get rid of the h squared term. So let's give it a try. And so we're essentially taking this whole series and subtracting 4 times the second series, and we'll want to combine the f primes together. Well, f prime of x minus 4 times f prime of x will be minus 3 times f prime of x, but minus a2h squared minus 4 times 1/4 times a2h squared will disappear. Let's put them together. I'm taking f prime minus 4 times f prime, and I'm taking a2h squared minus 4 times a2 times h over 2 squared, and then a bunch of other junk that starts with h to the 4th. Let's continue to reduce that. You end up with this linear combination on the left is equal to minus 3 times the derivative that we're trying to calculate, minus 0 because we aimed it that way to get rid of it, plus a bunch of junk that starts with h to the 4th. Let's solve for f prime. Well, I'm back to my nice computational formula again. I've got a computational formula, granted it's a little complicated, and I have an error term that is going to disappear like lightning. I mean, even if you have a h of 0.1, which would be pretty big, 0.1 to the 4th is 0.0001, and you get rid of most of your error by making the strategic linear combination. So that becomes now our computational formula, and we have an error that's getting really small in a hurry. Okay, so that leads us to some homework that you can do. I want you to go back to table 1 and write some pseudocode that you'll keep yourself. You don't need to turn that in. That reproduces that table. And then convert for item 2 that pseudocode to MATLAB and create an array. I'm calling it deriv for derivative. And just give me the contents of the derivative after you go through the iteration. Then what you'll need to do is expand your pseudocode to accomplish Richardson's method and add a 4th column, which is worth 20 points by itself, to see if you can even do better than what we have on that spreadsheet that was on that page. If you can figure out another formula to just get the order of h to the 6th term, then that'll be worth an extra number, 10 points. But I'm just asking for the next term, the one that will produce order of h to the 6th. And so that then concludes the section on central differences and Richardson's method. and we'll come back to this point next time.